Hello everyone, welcome to curve sketching. Alright, I know this video will get a ton of views because this is probably one of the more difficult topics we've talked about so far. It's just so much involved. So it's probably going to be a little bit long of a video, so strap yourself in, get ready for the ride, because here it comes! Alright, here we go, curve sketching. What to do. Alright, a lot of things we got to get in order to create this curve. First thing that I told you guys to check out was domain. Okay, you want to make sure that you at least have your domain written down somewhere just to, refer to. It will help you eventually. The domain for this, when you have a rational expression like this where there's a function on top of another function in a fraction, alright, is set the denominator equal to 0, and that's what x cannot be. That just gives you an idea of what a value of x that we cannot have. That'll help us later. Alright, so that's step one. Step two, alright, is you want to find your intercepts, your y-intercept, your x-intercepts. Okay, these take a little bit more work. The y-intercept is very simple. To solve for your y-intercept is actually just plug in 0 for everywhere you see an x. So if I plug in a 0 here and I'm plugging in a 0 here, I get 5 over negative 2. So negative 5 over 2. So that's my y-intercept. Very simple. For the x-intercept, you actually just take the numerator and set it equal to 0. So I'll write that here. 5 minus 3x equals to 0. Negative 3x equals negative 5. X equals 5 over 3. So our x-intercept is positive 5/3, comma 0. Okay, so there's your x-intercept, there's your y-intercept. Those are two easy things to calculate right off the bat, and those definitely will help you in curve sketching. Alright, the next thing you want to look at are for asymptotes. Okay, we have vertical asymptotes, and we have horizontal asymptotes. Okay, vertical asymptotes are when you set the denominator equal to 0. That will actually give you what your vertical asymptote is. Our vertical asymptote is also the same as your domain. It's just as written as x equals 2. That will give us where the vertical asymptote is. Horizontal asymptotes, there are 3 rules for horizontal asymptotes. Okay? Listen carefully. Rule number 1 is you look at the x in the numerator and the x in the denominator. There might be many, there might be none, whatever. You find that the highest degree, the x with the highest degree. So if we look at our numerator in this one, you notice that there's only one x and it's to the first degree. Alright, in the denominator there's only one x and it's to the first degree. So here are the 3 rules. If the degree of the numerator is bigger than the degree of the denominator, then there are no horizontal asymptotes. If the degree of the numerator is smaller than the degree of the denominator, then the horizontal asymptote is at y equals 0. If the degree of the numerator is equal to the degree of the denominator, then you take the ratio of the coefficients, and that is your horizontal asymptote. So when we look at our problem here, we have x to the first power, x to the first power, so they're the same, so I take the ratio of the coefficients. The coefficient for the top is negative 3, coefficient for the bottom is positive 1, so y equals negative 3 over 1. Or in other words, y equals negative 3. Alrighty, and now, after we find our vertical and horizontal asymptotes, the next step would be to take the first derivative of the function so that we can find our increasing, decreasing intervals, and then min-max, so on and so forth. So, we're going to take the first derivative. So, I'm going to do a little bit of side work here. This is the quotient rule. So, I'll say my numerator is my f of x, my denominator is g of x. Take the derivative of the top, take the derivative of the bottom, then I plug it into my chain rule, which says f prime times g minus g prime times f, all divided by g squared. Okay, so I distribute negative 3x plus 6 minus 5 plus 3x all divided by x minus 2 squared. 3x is cancel. I'm left with a nice 1 over x minus 2 squared. That's nice. Alright, so now I'm going to kind of use my paint to get rid of that, just so I don't have all that work there. So that means my first derivative is 1 over x minus 2 squared. Okay? Now, what we do now is we need to set the denominator, or we need to set the derivative equal to 0. That will give us our critical points so we can set up our intervals. Now, if you notice, we have no x on the numerator, which means that we can't set it equal to 0, but we can set the denominator equal to 0, and that'll give us what are the values that the derivative does not exist, but they are still critical numbers. So you would set x minus 2 squared equal to 0, which we know, if you just glance at it, that x can only be 2. That would be the critical number. So now we set up our intervals. We go from negative infinity to 2, and from 2 to infinity. Alright, the only critical number we have, so that's how we set it up. There's our intervals. Now we need to test a point in each of these intervals. I'll test 1 and 3. Plug them into the derivative and see what sign we get. When I plug in 1, I get negative 1 squared, which is positive 1, so I get a positive. When I plug in 3, I get a positive. So it's increasing. Okay? There are no extreme values, so there are min, and our max would be none. Alright, if that part confuses you, here's why. It goes from increasing to increasing. There's never a switch. If it switched from increasing to decreasing or decreasing to increasing, then we'd have a point at which we have a minimum or a maximum. In this case, we actually don't have one of those, so we would write none and none. So we got that. And now, what we need to do next is we actually need to find the second derivative so we can test for concavity. So I'm actually going to make the second derivative a little bit easier when I do this. I'm going to use the chain rule because I could actually, you could use the quotient rule if you'd like to. I'm going to use the chain rule. I'm going to rewrite my first derivative as x minus 2 to negative 2. I think it'll be a little bit easier. If you want to use the quotient rule, be my guest. You'll get the exact same answer. I just like to do it this way. So I know my second derivative comes out to be cubed. Okay, there's my second derivative. I take my second derivative, I set it equal to 0, and again, if you notice, there's no variable in the numerator, so I set my numerator to equal to 0, doesn't do anything in this case. Set my denominator equal to 0, we get x equals 2, which means that's our critical point for our second derivative. Put it into our intervals, 2 to infinity, the same intervals as our increasing, decreasing. Test a point in each of these intervals, 1 and 3. Plug them into the second derivative. When I plug in 1, I get negative 1 cubed is actually negative, because remember, cubing a negative number stays negative. Negative divided by a negative is a positive. When I plug in 3, I get 3 minus 2 is positive 1. That means negative divided by positive is negative. Alright, so we have concave up, we have concave down. Alright, which would mean that because it switches from up to down or down to up, we actually do have a point of inflection. But then you right as you're about to write that, okay? Because let's say you were to write this, point of inflection, because you guys are used to doing, the procedure. Our point of inflection would be at 2, right? So then you would take 2 and plug it into the original function, and then an alarm should go off in your head. You'd get a 0 down in the denominator. That's why I told you to write down the domain. Because you would have saw right away, 2 is not in the domain, so it cannot be a point of inflection. So in actuality, we actually don't have a point of inflection, even though it seems like we should. Because it switches from up to down, we don't. Okay, so there is no point of inflection. Okay? Alright. Alrighty. Now going to plug in, or I'm going to graph all of this information on my XY plane here. Okay. First, I want to graph the points, like I said before. 5/3, comma 0 is in between 1 and 2. So I'm going to put a point there. That's my x-intercept. 0, negative 5/2 is between -1 and -2 and 3. So I'll put a point there. My asymptotes are y equals -3 is my horizontal one. My vertical one is x equals 2. Alright, I'm increasing from -infinity to 2, so it starts from the horizontal asymptote, comes up to there, comes up, and then all the way up. Okay? It's also concave up, that's why it looks like that, which is awesome. And now, a lot of you guys would stop here, because you wouldn't think there are any more points. There's actually something else to do. If you guys were to plug this formula into a graphing calculator, there's another part to this graph. And it's actually down here, and it looks like this. Alright? That actually is part of the graph. How they come up with that is that it's increasing from 2 to infinity. Okay? It's increasing from 2 to infinity. So as we go from 2, which is the horizontal or the vertical asymptote, to infinity, it should be increasing, if you notice. It's concave down. That's why we have this little loop. And with that piece, with those two pieces of information, we can determine that it would be in between the vertical asymptote and the horizontal asymptote down here. The reason why I'm saying that is because if you were to put it over here, which is what some of you may argue, well, what about from 2 to infinity? Why couldn't it be like over here? The problem is that, remember, it always is approaching these asymptotes. The function will always be approaching the asymptotes. In order for this to be increasing in this area and concave down, that means it would look something like this if you follow my mouse. Okay? And it's concave down and increasing. That's not really approaching the asymptotes. Here would be approaching the asymptotes. We're approaching the vertical asymptote down here. We're approaching the horizontal asymptote over there. And if you notice, it's concave down and increasing. Okay, so that's kind of how you determine that. And again, you guys have the graphing calculators at your disposal. If you use the graphing calculator and saw, you would see that you got this part correct, which is awesome. But then you would see this other line, if you will. Alright? That's where you guys need to come up with, well, why is that there? How do I figure that out? And reasoning would tell you that it needs to approach each asymptote, and then that's why that's there. Okay? Thank you very much for watching, and I hope this helps. Bye.